Alright, so this video is going to be about examples of the cross and the dot product. So we introduced those and we did the conceptual framework for them in the previous two videos. So now it's time to do a few examples. So the first thing, let's just grab a couple of vectors. So everything in 3 dimensions, because cross products are only good for 3 dimensions. Let's grab a few numbers, so 3, 1, just whatever we want. And then V, let's do 0, 1, 2. As long as they're not collinear, because then the cross product wouldn't make any sense. But let's start with the dot product. So what would be the dot product of these two vectors? So u dot v would be, you grab the first entry. This is not a vector, so let's erase that first. So you grab the first two entries, 1 and 0, and you multiply them. 1 times 0, plus, you grab the second two entries, 3 and 1, and you multiply them together. That dot is a times. This is not the dot product, but it's just a times. And then let's do the next two. So 1 and 2, you multiply them together. And you get 1 times 0, 0, 3 times 1, 3, and 1 times 2, 2. You add them together, and you get your dot product. So the dot product is extremely simple, and that's why I didn't do much in way of examples, because it's just applying the formula directly. Now, we can do something like looking at what would be the projection of u onto the vector v. Well, remember the formula for that was, again, my dot products become that. I have a problem. Let's erase, I'll be right back. So it's u dot v over the length of u times the length of v. So this right here would be u dot v, which is 5. We already computed that, over the length of u and the length of v. So I need the length of u and the length of v to compute my projection, times, somebody forgot the vector v here, times v. Sorry about that, times v. That's the formula. Because this is just the magnitude of the projection, you need to multiply times the vector v. All right. And now what I'm going to do then is going to be, I'm going to compute the length of u. So the length of u is going to be the square root of the sum of all these entries squared. So the first entry is 1, 1 squared, plus 3 squared, plus 1 squared. So 1 squared is 1, 3 squared is 9, so 1 plus 9, 10, plus 1, square root of 11. And then the length of v will be the square root of the sum of the squares of the entries, or the coordinates of v. So 0 squared plus 1 squared plus 2 squared, which is going to be 1 plus 4 square root of 5. That square root's kind of funky. And then the projection onto v of u is going to be 5 over the square root of 11 times 5. Let's collect them together. 11 times 5, 55. I'll talk about that in a second. I could have left the 5 and just rationalized that denominator, but I'm not partial to rationalizing denominator. Sorry about that. So v then becomes 0, 1, 2. That's the vector I had, and then my projection is just the vector with entries. In this case, 0, 5 over the square root of 55. And as I said, I'm not partial about rationalizing, so I'm just going to leave it like that. So 2 times 5, 10 over square root of 55. And that would be how you compute a projection. All right, so now let's take a look at how you compute a cross product. So the cross product between u and v. So again, you're going to do your matrix with I, J, K. And you're going to put the entry the coordinates of u as 1, 3, 1, and then v. Now here you got to be careful, a little bit careful, not too careful, but a little bit careful about putting them in the right order, because if you put v first and then u, then you're doing the cross product of v times u, and you're going to get the negative of the result that you wanted. So just be careful with that. I'm going to augment this matrix with the first column and the second column. So I just grabbed these two columns and I put them on the side of my matrix to the right. And then to compute my determinant, I'm just going to go in the, say, call it the forward direction if you want. And in this direction, I'm going to get all positives. And in the backward direction, if you will, I'm going to make them all negative. So how does it work? Well, I'm going to grab my I, and I'm going to look at where I is located. It's here and here. So in the forward direction, so to speak, that's going to be positive. I want to multiply the coefficients that go in that diagonal. So 3 times 2. And then in the backward direction, I'm going to subtract. Whenever you go in the backward direction, you're going to subtract 1 times 1. And then I'm going to continue like that. Now I'm going to do j. So for j in the forward direction, I get 1 times 0, which is going to be 0. Minus j here, sorry, I did the wrong one. J is 1 times 2. And then plus k. In the forward direction, 1 times 1. In the backward direction here, 3 times 0. So why do you augment it by just 2 of them? That's just so that you have complete diagonals in the forward and backward direction for all of them. And then you get your signs correctly. Anyways, so that, what does that give me? That gives me 3 times 2, 6, minus 1, 5. So 5 in the I coordinate. Then I get 1 times 0, 0, minus 2. So I'm negative 2. Okay, ugly, but I'll write it like that. In the J coordinate. And then in the K, I get 1 minus 0. So plus K. Which you can always just write as, if you want, 5, negative 2, 1. So that would be how you compute your cross product. So we have done dot product, we have done projection, we have done cross product. Maybe we should do the angle between the two vectors. That would be another thing to do. Let's compute the angle, and then the last thing I'm going to do, I'm going to introduce another vector, and we will do a triple product. So there are other examples where we could do a application. So for example, torque, and I may do that. So let's think about that for a second. Let me work on the next one. So I'll erase this, and I will erase here so I can continue with it. So I'll be right back. You know what's worse than talking to yourself in public is disagreeing with yourself in public. So I said I was going to erase that, but that's going to actually be useful for me to compute the angle between the vectors. So I left it there. So why is that the case? Well, because remember that the cosine of the angle is going to be u dot v divided by the magnitude of u and magnitude of v. And we had already computed most of those elements, in fact all of them, because we computed the dot product to be 5 and this to be the square root of 55. We computed that earlier. Now, that is not the angle, that is the cosine of the angle, so I need to find the angle itself. Now, I got to remind you of one thing, and that is that when we define the arc cosine, we restricted the domain of the cosine to be between 0 and pi, so that the function would be 1 to 1. So between 0 and pi, whenever you do an arc cosine, you're always going to get angles in between this semicircle or the angle between 0 and pi. So if I do the arc cosine here, that's going to give me an angle between these two. So what does that mean? Well, whenever you have your vectors, there's always going to be one angle that is going to be smaller than pi, and that's going to be the angle you get from the arc cosine. So that is to say, there's really no worries here, like when we did the polar coordinates, that we had to be careful when we took an arc tangent to actually get the angle, the right angle. For the arc cosine, to calculate the angle between two vectors, there's no concern. So you would just plug this into your calculator. No need to add pi, no need to add anything. That right there would give you the angle. So now that I have disagreed with myself in public, let me erase this, and we will throw an extra vector, and we'll do a triple product, and then we'll wrap our video right there. All right, so with these three vectors, I'm not really going to draw them to scale, but let's imagine that we have three vectors. I'm going to put this one a little bit off here. So let's say you have vectors u, v, w. So what does that triple product we were talking about in the previous video, what does that give you? Well, that gives you, so if you grab this vector w, you place it here, and you grab a copy of u and place it here, also place it here, and then you place a copy of v here, and you place a copy of w here, and you place another copy of v here, and so forth and so on. You end up with a parallelepiped. Fancy word, isn't it? And what that triple product of u dot v cross w, what that tells you, that is the volume of this parallelepiped. And how do you compute it? Well, as we said, you just have to do the determinant of that matrix, but using all of the numbers. So you're going to grab u, I'm going to put it here, 1, 3, 1. Then v, which is going to be 0. By the way, the absolute value of this, because you may end up with a negative. I should have been careful with that. So we may end up with a negative, so we'll see. So the volume will be our absolute value of that. Oh, there's another thing I have to mention about cross product that I haven't mentioned. I just keep thinking about things to talk about. Anyways, so let's augment it and compute our triple product. So now we multiply in this direction. And so at this point, I don't have to factor things out because it's just numbers. So 1 times 1 times negative 1 is negative 1. 3 times 2 times 1. 3 times 2 is 6. 1 times 0 times 4, 0. So all these are the ones that go in the positive direction because I'm doing the positive diagonals. Now I'm going to go in the negative direction. So all those will be multiplied times negative. So this will be multiplied times negative, negative, and negative. So let's see what we get. So for this one, I get 1 times 1 times 1 again, so minus 1. 1 times 2 times 4, minus 8. 3 times 0 is 0, so minus 0. And so what do we get? We get negative 1 plus 6, 5, minus 1, 4, minus 8, I told you, negative 4. So we ended up with a negative 4. That's okay, that's the triple product, but the volume of this parallelepiped would be then 4 units cubed. All right, so that's one application for that triple product. And the last thing I'm going to talk about is the direction of the cross product. So we're going to talk about this here. The cross product satisfies the right-hand rule that if you have uv, when you're doing the cross of u to v, it's going to be pointing in this direction. So the cross product is going to be perpendicular, and it's going to be going in this direction. But now if you do v cross u, it's going to be pointing in that direction towards u. So in this opposite direction, you're going to have v cross u. And that's why they're negatives of each other, because they're telling you also a direction. So u cross v, it follows the direction of your thumb. V cross u, and you have to do this with the right hand. V cross u points out. And that's going to be a little bit annoying to you all because you're seeing the reflected version of this video, and I'm telling you I'm using my right hand, and you all think I'm left-handed because I write in a reflected image. Anyways, how about that to get your brain a little messed up? In any event, that is how this works. So I'm going to wrap it up here, and I'm sure we'll have other applications for physics later on this semester, so we'll add them as needed. Thank you for watching, and I'll see you in the next one.